Now we're going to look at graphs that are really helpful and graphs that are not, graphs that enlighten and graphs that deceive. The key concept, common graphs that foster understanding of data and some graphs that are deceptive because they create impressions about data that are somehow misleading or wrong, could be done on purpose or otherwise. Here's a dot plot and dot plots and its features. A graph of quantitative data in which each data is plotted as a point above some horizontal scale, and we stack them up. It displays the shape of the distribution, and it is usually possible to recreate the original list of data. It's important to understand what that means, the second part. That means you really have the data. Whereas when we look at the frequency distribution table, we don't have every piece of data. So here's a simple example. We want to construct a dot plot and find an outlier, if any. So the idea behind the dot plot is very simple, class. Okay, I want to make sure we understand what's happening. So at top here, you just come up with a line. You can call it number line even. You can come up with a number line even if you want. And now you look at the data and you come up with the scale that represents those numbers. And you can even, one easy way, whenever you want to do that, you can rank them from smallest to largest so you see what you have. And then you have this scale, you can, make up the scale that you want, something like, I don't know, 30, 35, 40, and you move on. So you set up, you make sure everything is covered. So for example, somewhere here, just to give you an idea, somewhere here is 80. So if you look at the very first number that is 80, I put a check mark at top of it. So I put a dot. I put a dot at top of 80. Now the next number is 94. Now I go find number, so this is, let's say, 85, 90, 95, and this one is 94. Then I put a dot for number 94. And I do that for every number. I stack them up. So if I have one more number that is 80, for example, just for the sake of argument, if I happen to have one more 80, then it goes at top of it, one more dot. I have one more 80, same thing, and again and again. I don't, but I said, if in case I do, you just keep on stacking them up. So if we do this carefully, it'll look something like this. So just as an example, I want you to see that number 56, we have two of them. That's why at top of number 56, there are two dots, and you can move on that way. So this is called a dot plot. Now, when we look at this, it appears there is a number that is way off, and that number is this one. It's way off, therefore it's an outlier. Now, it may be subjective here, but later on we give a precise definition as far as stats is concerned as to how we arrive at it. When we come across it, I go over that. There's a formula as to how we arrive at an outlier. We have outliers and we have extreme outliers, and each and every one of them has a formula. We go over that. But for now, just it appears that it's way off. And I think everybody's clear as to what we mean. That is a basic definition of an outlier, a number which is way out. Now, it's either too small or too large. But what does it mean objectively? That's what we're going to discuss mathematically.
Professor,
So,
sorry, I had a
yes.
question. So in regards to the dot plot, in regards to like the horizontal, like the categorical like range distribution, do we just kind of, was there a specific process you followed to figure out like, okay, 35 to 40, 40 to 45?
No, absolutely not. You can even start, okay, just make sure you have your smallest number, okay?
Okay.
The smallest number is covered. The smallest number is 36, am I right?
Okay, yeah.
Just make sure it's, so the smallest number is 36. And what was the largest number? 90, is that 94?
Yeah, 94, yeah.
So we want to cover all of those. So make up
Okay.
your own scale.
Okay, just making sure. Thank you.
Professor,
Yes,
could there be more than one outlier?
yes, of course.
Okay.
One of the things that happens, what statisticians do normally, they use trimmed data, okay, meaning they cut a percentage of the data from the top and the bottom, assuming we have enough data. Most of the time we may not. If we don't have that luxury, we don't. But if we do, they cut the bottom 5% and the top 5% to make sure there is no outlier. Okay, but you have to have enough data to do that. And yes, you can have more than one.
Okay.
Uh, Absolutely.
Thank
But
you.
as I said, as far as the precise calculation of that, we'll see it later on how it's done.
Okay. Thank you.
Sure. All right, we're going to look at a different graph known as stem plot using the same example. Could somebody read that one for us?
Stem plots represents quantitative data by separating each value into two parts, the stem such as the leftmost digit and the leaf such as the rightmost digit.
Perfect. Could somebody read that for us?
Features of a stem plot shows the shape of the distribution of the data, retains the original data values, and the sample data are sorted or arranged in order.
So what happens in this case, you really look at the data and you see there are two digits. Because there are two digits is fairly easy to pick. You look at the leftmost digit and the rightmost digit. You basically have a horizontal line and you go from the smallest to largest and you see the smallest number was 36. So let's start with 3, 4, and you go all the way to 9. So as an example for 80, we would write 8, and then to the right of it, we write the second digit, which is 0. Now let's stick with 80. The next one is 94. So that's 94. But I want to go back to 80. Anything that are in 80s will go next to this one. For example, the next one I see 82. If I'm dealing with 80s only, then 8, 0, I'm going to write number 2. Now, we better go with the order, but let's stick with the 80s. Let's see what else we have. Let me just circle the 80s. We have 86, we have 88, we have 84, and I believe that's it. So now, even if you don't put it in order, it's okay, but it's a good practice to put it in order. So the next one would be 84. The next one would be 86. And the last one would be 88. And that would be for 8080. That means, so if I were to read this from here, I should be able to get all my data back. I have numbers 80, 82, 84, 86, and 88. Now you do the same thing for all of them. So I hope it is clear as to what we have here. So stem plots and dot plots, they give us the whole data and the graph.
Question.
Yes, of course.
Um, would there be situations where the number would be like 82.5?
Yeah, I don't think for a case like that they expect you to do the stem plot, but yeah, it could be, or the number could have 5 digits, and probably you cut it into 2 and 3 or 3 and 2. You know what I mean?
Yeah.
So the point being is the type of data that you are given, it makes it possible to do an easy stem plots. Okay, that's the concept.
Okay.
But yeah, I mean, for the sake of argument, if it's given as 88.7, you would put 8.7 on the right side. Okay.
So how do you separate them out in that case if there's like decimal points involved?
Again, you can't. I mean, if you are using the first digit as 8, and that is what you have to do, then if it's 88.7 on the right side, so the way you separate them, this would be 8.7. Okay, it's important that you have a gap. So 0, 2, 4, 6, 8, and the next one is 8 point, let's say 7, because it was 88.7. But normally, again, it doesn't happen, class, because the purpose of the stem plot is to make sure you are dealing with the type of data that can be written in that format. And more importantly, they may actually give you this one. and then you come up with the original data. Okay, so I wouldn't worry about that. The bottom line is to make, in essence, make life easier writing the numbers, okay, and making it easier to understand. So the concept is when you're dealing with the 30s, there's only one number. When you're dealing with 40s, there are no numbers. When you're dealing with the 50s, there are three numbers. When you're dealing with the 60s, there are one, two, three, four, five, six numbers. That's the idea of the stem plot, being able to see and recognize that. Now, the next one is a time series graph, a graph of time series data, which are quantitative data that have been collected at different points in time, such as monthly or yearly. Normally, they reveal some sort of a trend over time. So with that being the case, here's an example. We are given women's median earning as a percentage of men's median earning from 1990 to 2010, and we want to see what's happening. Do we see a trend or not? So from 1990 to 2010, you got to plot the point, and then you can connect them with line segments. The idea is that you want to see what happens, what the trend is. I'm going to assume everybody can do the graph. We are graphing and along the horizontal line. The first one, let's say here is 1990, and then maybe you go to 1995 and you move on. Okay, some sort of a scale you use. Okay, or maybe use, if you have room, you use scale such that along the horizontal axis you have 1990, 1991, too. That would be the best, of course. Okay, if you could do that. And on the vertical side, then you have the scales from 0 to 100, because we are looking at a percentage, and you plot the points. I'm assuming everybody can do this. It's not a big deal. So along the horizontal axis, we have the years starting from some year, and we move on. And along the y-axis, the vertical axis, we are given this percent, which represents women's median earning as a percentage of men's median earning. Is there any trend as we look at this graph? Does it appear to be a trend here? Anybody can notice any trend? What do you think?
Yeah, it increases.
Very good, it's going up. There seems to be that it's going up. And so the effect is that it could help close the gender gap when it comes to earning, according to this data. The bar graphs are similar to histograms. Graph of bars of equal width to show frequencies for categories of categorical or qualitative data. The bars may or may not be separated by small gaps. It shows the relative distribution of categorical data, so it's easier to compare different categories. It's very similar to histogram. Now, a Pareto chart is a bar graph, then it has an added condition. We put the bars, we arrange them in descending order, of course, according to the frequencies or percent frequencies. So therefore, the height goes down as we go from left to right. And again, it has the same feature. So here's an example. We want to construct the Pareto chart for this example. Can somebody read the question for us, please?
A study of retractions, admission of wrong claim in biomedicine showed 472 were due to error, 225 were due to plagiarism, 881 were due to fraud, 295 were due to duplication of publications, and 249 had other causes. Construct a Pareto chart. Among such retractions, does misconduct, fraud, duplication, plagiarism appear to be a major factor?
Thank you so much. Obviously, it's fairly easy to come up with the chart. I don't think anybody has any problem with the chart. I want you to pay attention to the numbers. 472, 225, 881, and 295, and finally 249. So we want to go from the largest, which is 881, or due to fraud. That would be the very first bar, and that's the largest. So along the horizontal axis, we put the categories. What are the categories? Would be fraud as the first one. Then which one is the second largest is 472. So this would be the first bar. This would be the second bar. Then we have 295 duplication. Okay, so everybody gets the picture. So that would be the horizontal axis. What is the vertical axis? Those numbers. And that's what we get. And I don't think one needs much to understand the situation. And clearly, when it says among such retractions, does misconduct appear to be a major factor? Obviously. The good old pie chart, everybody knows what that is. We've been dealing with that from, I think, elementary school. I hope everybody is comfortable with that. It's a very common graph that gives us categorical data as slices of a circle in which the size of each slice is proportional to the frequency count for the category. So how do we come up with this slice? Is 360 degrees times the percentage that you need to come up with, if you will. That gives you the angle, if you will, that you need for the wedge. And so with that being the case, we want to look at this case, and to come up with the pie chart, you need to know what is the total. Just as an example, if we look at 881, so the percent that we need for that one, okay, remember, you come up with a circle, and then you want to cut it into pieces. Okay, remember, this is 360 degrees when it covers the whole plane. So you have to divide 881 by, and now all of them, what is it, 472 plus 225 plus 881 plus 295 plus 249, and change this to a percentage. So 881 divided by the sum, that gives you the percentage. And you multiply it by 360 degrees, and that gives you the angle you need to represent the amount of fraud, if you will. So take a look at this. If you multiply this by 360 degrees, and I'm going to leave it for class to figure out this angle, okay? And wherever you put that and however you put that, it makes no difference. Now, you can do the same calculation for each and every one of them. The next graph we want to look at is called frequency polygon. Could somebody read this one for us, please?
A graph using line segments connected to points located directly above class midpoint values. A frequency polygon is very similar to a histogram, but a frequency polygon uses line segments instead of bars.
Thank you so much. A relative frequency polygon is the same thing in essence. A variation of the basic frequency polygon is the relative frequency polygon, which uses relative frequencies, proportions, or percentages for the vertical scale. This is an example of a graph. Let's look at an actual example to see how we go through the process. First, let's come up with the histogram. I don't think anybody has any problem with that. In order to come up with the histogram, remember, you know how to do that. And we have the boundaries. For example, the first one is 5.5 to 10.5. The frequency is 1, so the height is 1, and so on and so forth. We want to come up with that using relative frequency. If we wanted to come up with the histogram using the frequencies, we would use the second column. Now we are told to use the relative frequency. So that's what I mean. You want to be very careful when you read the question. So relative frequencies are defined as f over n. So this column you have to divide by the total. First, you have to figure out the total. When you add up this column, you get n equals summation of f, and that's 20. So you divide this column f by 20, 1 over 20, 2 over 20, and the rest of it. And they obviously must add up to 1 or 100%. Now we have the horizontal axis, 5.5 to 10.5 to 15.5, all the way to 40.5. The heights are for the first bar, 0.1 0.05, the second one is 0.1, and so on and so forth. So my assumption is everybody is very comfortable coming up with this histogram. So that takes care of the first one. The next one is the frequency polygon. So this question is asking for the histogram. Is taken care of. So how do we come up with the polygons? We need to look at the midpoints and connect them. So understand what are the midpoints. The midpoints really in essence starts from here. This is the midpoint for the first class. Now how do you come up with that? 5.5 plus 10.5 divided by 2, or 16 divided by 2 equals 8. So that's number 8. That is the midpoint for the first one. And right at top, it's here. The next one, you can calculate or just add 5. The width is 5. So add 5. You don't have to calculate all the midpoints. Just the first one is 8. And the next one, just add 5. Keep on adding 5. So corresponding to that is this one, and then this one, this one. So first, let me look at those. So you connect those with line segments, everybody. Also, you really have to extend this to the left. So now you really go by the width of 5 here. I want you to know that. And you connect here. Same thing here with the width of 5. And you connect here. Okay, you add, if you will, 5. So that's the polygon. So it looks something like this when you're done.
Professor, I just have one question.
Yes.
To the beginning and the end of the graph,
Yes.
you have to add half of the width. Is that
Yeah,
what it is?
let me just go back and show you what I mean by that. First, connecting those parts, the midpoints was clear. Now remember what's happening. If this number is 8, right?
Yeah.
You can go 5 units to the left. That's one way to do that. It gives you 3. Or from 5.5, go half of the width, 2.5 to the left. Either one leaves you number 3. Is everybody clear?
Yeah, thank you.
Sure. So look at this one. Remember what's happening. From 8, you go to the left, and from 38, you go to the right. Now, from there, the midpoints, the first midpoint minus the whole width. The last midpoint plus the whole width. So this one you add a width. This one you subtract a width. Okay, as far as knowing precisely where you end up. Does that make sense to everybody?
Yes.
All right.
Yeah.
For
Let's
the
go.
frequency polygons, do you always use the midpoint?
Yes, yes.
Okay.
This is how we graph polygons. All right, let's go to ogive. Now, in order to come up with the ogive, the very first thing you have to use is a cumulative frequency distribution table. So you got to come up with that. So first, this is the given. There's nothing brand new. But how do you come up with the cumulative frequency distribution table? If you recall, I said just either use the boundaries or limits, whatever is given. In this case, the boundaries are given. Okay, so you keep the lower limit, in this case, the lower boundary of the first class, and it becomes the lower boundaries for each and every one of the classes. And the upper boundaries remain intact, and then you add up the frequencies. The first class, the frequency is 1 and it doesn't change, but the rest of them you add up. So first you write them in this fashion. The lower boundaries all change to the lower boundary of the first class. So this 5.5 will take over as the lower boundaries for each and every one of those. The upper boundaries remain intact. Now, what about the second column? Again, the first one doesn't change, becomes 1, but the next one is 1 plus 2, and then you keep on adding. So those are the frequencies. But remember what we had. We were supposed to do this for the relative frequency, and therefore, we are going to divide this again by n. And the last one, it's extremely important to remember, the last one is always 1 or 100%. The last one is always 1 or 100%. And so we have this. Again, this shouldn't really take that long for you to figure out. We have gone over that. I just wanted to go through the procedure to remind you. So we have that. So we have the class boundaries for the cumulative frequency distribution table. We have the frequencies, and we are interested in relative frequencies. Now, how do we come up with the ogive? The way the ogive works, again, you put the boundaries on a horizontal line, and you put the frequencies or relative frequencies. In this question, we are putting the relative frequencies, okay, on the vertical line. So construct an ogive. It's a line graph that depicts cumulative frequencies. So ogive goes with cumulative frequencies. And ogives use upper class boundaries and cumulative frequencies or cumulative relative frequencies of the classes. What do we mean by that? The lower boundary of the first class, okay, so you have your horizontal line, you have your vertical line. Your horizontal line are the boundaries, end of the story. What about the vertical? The vertical lines is either the frequencies or relative frequencies. And which one are we using for this question? The question was asking for relative frequency. That's why we're going to use that. But you have to read the question and make a decision accordingly. So with that being the case, we are going to use the relative frequency. So we go from the smallest to largest, or relative frequency or percent frequency, it doesn't matter. So 0.05 or 1 out of 20, okay? And you keep on going all the way to the end, and it has to be 1. So how does this work? How do we connect the line segments? I want everybody to pay attention to the lower limit of the very first class corresponds to 0. The upper limit of the very last class corresponds to 1 or 100%. Everything else goes in between, putting together as line segments. What lower limit of the first class is 5.5, and it corresponds to either 0 or 0%, depending upon whether you're using the frequency or percent frequency. Upper boundary of the last class is 40.5, and this number corresponds to either 1, or if it's a percent frequency, 100%, or if it's frequency, this must correspond to the value of n. In other words, if we were doing the frequencies, that would be number 20. So those are the first thing I want everybody to understand. So the lower limit of the first boundary corresponds to 0%. The upper boundary of the last one corresponds to 100%, or n. What happens afterwards? You look at the upper boundary of the first class. So the upper boundary of the first class is 10.5. And that corresponds to either 1 or 1 over 20. So look at this number. At top of 10.5, you either have number 1 or number 0.05. You use 1 if you're dealing with frequencies. You use 0.05, and we are going to use 0.05 here if you're dealing with percent frequency or relative frequency, okay? Now, for 15.5, you put 3 or 0.15. For 20.5, you put either 6 or 0.3. For the next one, you
Professor,
put either 11. Yes, go ahead.
I have a question. Is it going to tell us when it's cumulative relative frequency on the y-axis, and then we know whether to put 3 or 0.15 or
yes,
6?
The question, if you go back to the question that we did, previous page, it said specifically relative frequencies, and I underlined it.
Okay, thank you.
Sure. Now, what is it good for? It can help us answer a question such as this one. What percent of runners ran 22 miles or less? In which case, Along the horizontal axis, you locate number 22, and along the y-axis, you do your best to find the answer, and it's about 41%. All right, now graphs that deceive. One of the problem is a non-zero vertical axis. A common deceptive graph involves using a vertical scale that starts at some value greater than zero to exhibit differences between groups. Okay, for example, in this case, we notice it starts at 10% OxyContin and placebo.
Sorry, Professor, I think I have a question on that last slide.
Go ahead. What's your question?
I was curious, could you change the width to make it fit the 22 miles?
I'm sorry, what about 22 miles? 22 is a number between 20.5 and 25.5. Now, what is the
boundary? Could you change the width to make it less than 22?
Okay, you want to make the width smaller than 22. Is that what you're saying?
Yes. Could you do that, or that was the part I was confused on?
I'm not too sure if I follow the question. The width is 5. If you look at the class boundaries, the width is 5, and that remains constant for each and every one of the classes. When you refer to the width, you're referring to the width of the class. Am I right?
Yes.
Okay, the width of the class is 5, and you can't change it.
Okay, I was just curious. Thank you.
Sure, sure. All right. So if you have a non-zero vertical axis, that is one that is really not a good idea. Take a look at what happens when we use the proper axis. Take a look at the change, 10%, which is wrong versus 0%. When you look at the 10%, it appears that the placebo has basically no effect. So it is extremely important to be careful with. So always examine a graph carefully to see whether a vertical axis begins at some point other than 0. Also, when we look at pictographs, first of all, drawing of objects called pictographs are often misleading. Data that are one-dimensional in nature, such as budget amounts, are often depicted with two-dimensional objects or three-dimensional objects, and that is not correct. So by using pictographs, artists can create false impressions that grossly distort differences by using the simple principles of basic geometry. When you double each side of a square, its area doesn't merely double, it increases by a factor of 4. In other words, 2 squared equals 4. When you double up, you multiply the area by 4. When you double the side of a cube, then it's 2 cubed. It's 8 times larger. 2 cubed. That's how we arrive at the 8. So when you look at this case, this is misleading. A one-dimensional data with a three-dimensional data. This is a fair and objective pictograph, which is a data that is using very simple bar graph and clearly give us the exact situation starting. Pay attention that starts with 0. Whereas if you look at the left side, it appears there's a huge difference between the two. When you multiply it by 4, it gives you this proper graph. When you do it here, 4 cubed, because it's three-dimensional, it appears that it's 64 times larger, which is not proper.